and the direction perpendicular to that, the plane perpendicular to that, is called the transverse. So TE, which is basically transverse electric wave, is a wave where the electric field component only exists in the transverse plane to the direction of the propagation or the longitudinal direction, but there is a longitudinal component of the magnetic field. With respect to that, we can also have waves which are transverse magnetic waves or TM waves, in which case we would have an H field, an E field which is perpendicular to that, and a component of electric field in the direction, in the longitudinal direction. So this is a wave where the magnetic field H only has a component in the transverse plane to my direction of propagation, whereas the electric field has a component in the longitudinal direction too. And we may have TEM waves only in very, very certain conditions where you just have EX, HY, and no component in the Z direction. We had seen what will happen is that when I have these components EX, this component for the transverse electric wave would have to vary in y direction, will have to have an amplitude which varies in y direction, whereas the H field y will have a component also which would vary in y direction. If a field points in one direction and its amplitude varies in the 90 degrees in the perpendicular direction to that in the transverse plane, then the Z component of the other field would always exist. On the other hand, if a field varies in the same direction in its pointing towards, then its own component would exist, which is happening in this case too. So the EX would vary in y direction in amplitude, HY would vary in y direction too, and HZ would be present, and in this case, HZ would also vary in y direction. For the TM wave, similarly, HX would vary in y direction, EY would vary in y, and I would get EZ, which would be existing towards that. For TM fields, ENX EXHY has no amplitude variation in XY plane. And as we will look at the solutions, we'll start looking at a specific solution today, the transverse electric field for uh, parallel slab waveguide. We'll see that these solutions are actually different in their shapes. And not only that, depending on the geometry, the velocity with which these solutions will travel would also be different. So they start to create some kind of variation of my variation of the electromagnetic field within my waveguide. These were the main pertinent points from yesterday's lecture. Let's see if we understand these points, and I have three questions. Can you see my questions well? So the first question is, you have been given a electromagnetic field variation. You have been given how the wave looks like, and you've been asked to identify what kind of wave that is, whether it is a TE-TM or a TEM wave. The first part of the question is, which direction is the wave propagating in? So you have to start looking for certain elements, certain characteristics, mathematical signatures within that function to try to understand which direction the wave is propagating in. And then we have to figure out whether this wave is propagating in is this wave propagating TE, TM, or TEM. Why don't you think about it for 30 seconds and let's see if somebody can give me the answer. So the first question, which direction is the wave propagating in? I see if somebody's hand was standing up. Like if anybody has an answer, can come up and speak up. Let's see if the class agrees with that or not. What are we looking for here? We are looking for terms which are of the form, again, remember from last year, a wave has to have an argument which is given by t minus z by vp. We're looking for an argument which has that specific form. It has to have a form, and then we had said we had specifically looked for wave which was sine or cosine, which was of the form of omega t minus beta z. So for the wave to propagate, this has to happen. The wave, the argument function should have both the time period, both the time and the distance. And in this case, what the only function which has that is this function over here. So this term over here must be omega. This term over here must be beta. And the term which is coming here, this must be the direction in which the wave must be propagating in. So the wave should be propagating in y direction as it is here. The electric field of the wave is pointing in x direction. So y direction is now my longitudinal direction. And x and z, the directions perpendicular to that, are my transverse directions. So the wave is propagating in y direction. It has an amplitude variation, but that amplitude variation is also happening in y. So that is nothing but an attenuation constant. That is saying that as the wave is propagating forward in y direction, its amplitude is decreasing. It's giving some of its energy to the medium. It's heating up the medium most probably. It's giving some of its energy to there. And because of that, it's losing its amplitude. But that's not amplitude variation. That's not bounding of the wave. That's not guiding of the wave. That's not saying that the wave only is only confined within a specific region in the transverse direction, which is what the wave guiding effect is. So we have an electric field E, which is pointing in x direction. It's propagating in y. As it's propagating in y, it's giving some of its energy to the medium. But is this electric field confined in x or z direction? Is there any variation in x or z? There is nothing in the function which says that there is any variation in x or z. So basically, this E is plane in transverse direction. There is no variation happening of this E in the transverse direction. There's no amplitude changing in the transverse direction. Which wave should it be? Because the electric field is not varying, it's not varying in the transverse direction at all. The only magnetic field which would exist would be perpendicular to that. There won't be any electric field or magnetic field components in the propagation direction. So the wave is a TEM wave. Without doing maths, we need to be able to look at these functions and be able to see what these functions represent. That's how you start to really understand what the waves are doing. So this is a wave which is propagating in y direction. As it is propagating, it's losing some of its energy in y direction, but is unbound in the transverse direction, has no variation in the x z direction, which is the transverse direction, and hence this would be a transverse electromagnetic wave. There won't be any components of EY or HY in this case. Let's go to the second question of the same form. Having gone through the logic before, can you tell me whether this is a TEM or a TEM wave? Which direction is the wave propagating in, and whether it is a TEM or whether it's a TETEM or a TETM or a TEM wave? Again, look for that imaginary component in the phasor term. That would tell you the direction in which the wave is propagating. Once you determine that direction, the other two directions would be the transverse components, and then try to see what's happening in the transverse components. So there are three terms here. You have a term J beta Z, which is your phasor term. Again, remember beta has to be J. We are in phasor term. This is being multiplied by Ej omega t, and you have omega t minus beta Z, which becomes your wave. So this part is telling you the propagation. This part here is saying that as the wave is going forward in Z, it is losing some of its energy. This is an amplitude variation in Z, the same direction of propagation. This part is your attenuation. And then it's basically saying that your X, Y planes is the transverse plane, and it's saying that if I take a look at this term here, it's saying amplitude varies in X. So it's telling you you have an electric field. This part here tells me that the vector is pointing in y direction. So this electric field is the EY component, and this EY component has an amplitude variation in X and an amplitude variation in Z. This part is nothing but the propagation. I expect an amplitude variation happening there. But it's saying that I have an EY component which has an amplitude variation in the opposite direction towards its pointing in the 90 degrees direction or the perpendicular direction towards where it's pointing it at. So there must be HZ component too. If a field is pointing in one direction and its amplitude is varying in the other, the Z component, the propagation longitudinal component of the other field should exist. So Hz is existing, and obviously Hx will exist. So the three components which will exist would be Ey, Hz, and Hx. So it's telling me that there is a component of the magnetic field in the direction of the propagation, but no component of the electric field in the direction of propagation. So this must be a TE wave. Always, whenever you're looking at any wave functions, and many times when you're doing some solutions yourselves too, as you'll see, the maths we'll do will become complicated very soon. Um, Even when I'm doing my research with waveguides, many times the maths becomes very, very complicated, and the final answer, it's very difficult to see whether the final answer is absolutely correct or not. And then what you should get into habit of is always looking at the final functions and see whether that makes sense, whether that is the kind of solution you're looking for. So figuring out what these various terms in a mathematical function physically represents helps you learn, helps you understand these waves and these waveguides at a much deeper level than just doing the maths of it. And in this case, again, you you always look for the direction of propagation. So it's very clear that the direction of propagation is E minus j beta z. That's the term which I'm looking for. That's the propagating term. It's saying that there is an attenuation of the wave as it's going forward, but it's saying that the amplitude is varying in the x direction and the field is pointing in y direction. As soon as I have that information, I get the answer very quickly saying that because the field is varying in perpendicular direction, perpendicular transpose direction, the opposite field z component should exist, hz should exist, and hx should exist. You can then do the maths and calculate what those values are, but it makes your life so much easier if you physically understand these things. All right, last question before we start the new topic. What about this case? Similar function, except a small change. These terms haven't changed. This term here has changed. So it's telling me my E now has a direction of Y and is varying in Y and Z. Again, remember the arguments we put within the brackets is how the amplitude is changing. And we'll keep on using the numbers throughout. And the argument we put here, the subscript we put below, is the direction of vector. Which component are we talking about? It's basically saying that this electric field vector is pointing in y direction. So we just write E subscript of y to remind us that the electric field is pointing in y direction. So I have a field which is pointing in y direction and is also changing in the same direction. So that tells me that Ez should exist. If a field points in a direction and the amplitude of the field varies in the same direction, the longitudinal component of that field has to exist. Ez should exist and Hx will exist. Ez would again have a variation of yz, Hx would again have a variation of yz. And again, the argument we said before that if a field exists and points in 90 degrees to it, the opposite component of the other field, the z component of the other field should exist too. So if hx exists and changes its amplitude in y, Ez would exist. If Ey exists and changes its amplitude in y, Ez would also exist. So everything is nicely uh, pointing towards the same arguments. So this wave should be a TM wave. Any questions? Any questions or all right then. Let's start the let's start learning more. Let's start looking at what we wanted to do today. And what I want to do today is mathematically find the solutions of one specific mode and then see what that solution means. We'll come up to some very interesting results. Again, the solution we are looking for is a parallel plate waveguide. Basically, we are saying that we have two very large conductors, almost like parallel plate capacitors, which are separated by a distance. Let's call it A. So this is a conductor, and for the time being, we'll assume that these are perfect conductors. And we want to, we said, for the sake of defining the scale, let's define this to be x direction, this to be y direction, and the propagation direction to be z. We said we want to find a solution where I have an electric field E which is pointing in x, and because the electric field has to be zero here and has to be zero here due to conducting boundaries, because this electric field has to be zero at these boundaries of the conductors, otherwise the charge of the conductors would distribute itself till the induced electric field cancels any electric field there. Because this electric field has to be zero at the two places for any solution to exist, it means that the electric field should have an amplitude variation going in the y direction. So there must be an amplitude variation in y. We had said we want to look for a solution where, because as soon as I have Ex and Y, it tells me that there must be an Hz component, and there obviously would have to be an Hy component, which also varies in Y. And I'm looking for a solution which is propagating in Z direction. I'm looking for a wave which is propagating in Z direction. So this has to have the argument of Z. So we're looking for solutions. We are looking for what these values Ex, Hy, Yz, and Hz, Yz look like. That's what the answer we want to. That's the answers we want to get into. Again, we are looking for propagating solutions. We are looking for solutions which have E minus gamma Z in them, where gamma in general is alpha plus J beta, where alpha is your attenuation, how much the energy is lost going through, and beta is your propagation term. So we're looking for solutions which have the form E minus alpha Z, E minus J beta Z. Just so that we don't have to write the whole thing, we're just gonna call a term called gamma. We're gonna represent it by a gamma, and then we will substitute later where we want what do we want to do. So we are basically looking for the forms which are, we said that it's going to be Ex and Yz. It's going to be of that form, Ex and Yz. There would be a variation in X direction, but we are looking for solutions which are propagating in Z. So the solution has to be of this particular form. There would be a variation in Y. I'm still looking for, let me make it a bit clearer. I'm looking for specifically these solutions. Again, we have two equations we can use. These are the Helmholtz equations, which was del square xy z e xy z plus omega square mu epsilon e is 0, or del square xy z h xy z plus omega square mu epsilon h is equal to 0. These are the two Helmholtz wave equations. We can use either one of those to find a specific solution. And it's, as I had talked to you about it yesterday, I said it's always easier to find the electric field than the magnetic field terms. In the magnetic field terms, you have to really, really understand everything. Whereas electric field, the boundary condition is very simple on the conductors. If there is an electric field which is parallel to the conductor, the electric field has to be zero. So we know, and again remember, these different are interrelated to each other. Once we define one specific field, the other two fields will have to take a specific form. They cannot be independent of each other. That's the Maxwell's equations. All these three fields are interdependent on each other. So, because we know that this electric field E is parallel at this boundary condition, and we know that this field has to go to zero here, and this field has to go to zero on the top. It's actually easier to start using this field and then come up with a solution. Some of the textbooks you read may actually do the solution in HZ and then create another boundary condition. I'll talk about that solution very, very quickly later on, how to do that. Uh, but it doesn't matter which way you start with, the final answers always turn out to be exactly the same. So I will start, I always like to start with the electric fields, and I look for the component of the electric fields in the which are parallel to the boundaries of the conductor boundaries, because I know that the electric field has to be zero there. So I will look for a solution of the electric field Ex, which I know has to vary in y and z direction. So what I want to do now is, for this geometry, I have a parallel plate. Let's call this is your x plane, this is your y plane. I want to find a solution del square E plus omega square mu epsilon E is 0. I want to take this and I want to solve this problem. And I have del square, as you probably remember, is del by del x square plus del square by del y square plus del square by del z square E plus omega square mu epsilon E is 0. Again, remember, we know E is varying, is pointing in x direction, is varying in y direction, and is propagating in z direction. That's the solution we are looking for. So from this function, it is very clear that this term over here is not going to exist. When I take the derivative of the electric field with x, there's no variation happening in x. So this term is going to be 0. There is not going to be any variation which is going to happen in the x direction where these conductors are very infinite. And if you think physically, that should be true also, because if the answer was changing in x, then whether I put the origin here or whether I put the origin axis here, the solution would change. And that makes no physical sense because the problem has not changed. When I am on my left axis, I have infinite conductors on the left hand side and infinite conductors on the right hand side. And when I go to the next axis, I still have infinite conductors on my left hand side and infinite conductors on the right hand side. The problem mathematically looks the same whether I'm here or whether I'm here, whether I'm in the first line or the second line. And thus, I know for sure that the solution should not vary in x direction. So only del by del y square and del by del z square should exist. Again, the advantage of exponential functions is when you take a derivative, all you do is you get this term out. We take the derivative twice with z, so we'll get minus gamma square out. So that term then becomes d square e x y by dy square e minus gamma z plus I get minus gamma square exy e minus gamma z plus omega square mu epsilon exy e minus gamma z is equal to 0. I can drop these exponentials and I end up getting a simple equation which I need to find the solution for, a second order differential equation, d square ex by dy square plus omega square mu epsilon plus gamma square exy is equal to 0. That's a second order differential equation and I need to find the solutions for this term. Before we find the solution, let's define the origin of our axis. Where does it help me to put the origin? And in fact, when we do various waveguides, depending on how you choose the origin, if we get to dielectric waveguides at the end of the course, if time permits, you'll see that the origin choice would be quite different than the origin choice we use here. I know that the electric field E x at this place has to be 0, and the electric field Ex at this place has to be 0. That when I go to this bottom boundary, the electric field at these two places have to be 0. This is my boundary condition. This is my conducting boundary condition. So it helps me to put my origin, to put my x-axis right on one of the conductors. So it helps me. I want to make my maths as simple as possible. So it helps me if I say that my x-axis is right here and my y-axis goes from that point. It doesn't matter which point I choose in the lateral direction and the horizontal direction because that all these points are the same. But it helps me to put the x-axis exactly on one conductor. So then I have a boundary at the bottom where y is equal to 0, and I have a boundary at the top where y is equal to a. So it's telling me that I have a solution which now I have to find. Again, just let me redraw the waveguide and my axis. It's telling me that whatever solution I have, which is pointing in x, when y is equal to 0, has to be 0, and when y is equal to a, this has to be 0 also. That's the boundary conditions. These are your boundary conditions provided by that thing. So I have to find solution for d square exy dy square plus omega square mu epsilon plus gamma square exy is equal to 0. I have to find a solution for that term. Again, remember, this solution is whatever the answer I get has to be true for any values of y I have within 0 and a. So it's saying that the second order derivative of the function has to be some constant multiplied by the function itself. So that I can take the function out and I can make my answer go out, right? And this is a problem you see in engineering a lot, the second order differential equation. You see in engineering a lot, and you know that they are, and we had talked about this in last, you must have talked about this a lot in last term, and you must have seen this function also in your transmission line. And you know there are only three mathematical solutions to this function. One is a linear variation, which basically says that the function should vary linearly with y, so that when you take the second order derivative goes to 0, and whatever is in the front of your function, whatever is the argument here, that should be equal to 0, which is not a solution we are looking for. And the other function is either a sine or a cosine or an exponential form. When you take the derivative of sine, you convert it into cos, you take the derivative again, it becomes sine again, the function comes back. Or if you take the derivative of exponentials, you just keep on getting the exponential back and back as many times as you do the derivatives. However, sine and exponentials are again related to each other. You can uh, convert sine function to exponential functions very easily, so they're not really any different function. So we know, looking at this, that the solution exy has to have a form of sine and cosine. Let's call this term over here so that I don't have to write that whole term again. Let's just call this h square. So h square is omega square mu epsilon plus gamma square. So the function has to be a sine hy plus b cos hy in general. This is what the solution has to be. And this solution has to obey the boundary conditions we have determined. This solution has to obey these conditions. Have to obey these boundary conditions. Again, you can convince yourself, just do a simple mathematical exercise. You substitute you substitute the terms into the derivative, you will see that you'll basically get h square term out, and you can convince yourselves that this would be the exact solution. So let's now to account for the fact again. Remember, the Helmholtz wave equation was only derived as a point form for a homogeneous medium. This is not a homogeneous medium, so we now need to bound the solution. We need to create rules for the solution based on what we are seeing at the boundaries. So let's apply the boundary conditions. And at y is equal to 0, my function has to be 0. So Ex at y is equal to 0 has to be 0, which is a sine of 0 plus b cos of 0. A sine of 0 is just 0, but b cos of 0 is b, which tells me b is equal to 0. That this cos form cannot exist. There cannot be a cos form. And you can convince yourselves, because if this cos form existed, it tells you what would the cos function look like. The cos function, the first order cos function, would look something like that. And if the cos function exists, it's telling you that the electric field is existing at that boundary, that the electric field is not zero at the boundary. That makes no sense. That makes no physical sense. And maths is telling you, yes, that makes no physical sense. This function, this cos term, cannot exist. The only term which can exist is a sine term. Again, remember what the sine term would look like? Would be something like that. The first order sine term would be something like this. So the sine term will exist, but the cos term will not. So now my solution looks like Exy is some constant A, which is your amplitude constant, what the amplitude of the electric field is going to be, multiplied by sine Hy. And if you want to put a vector to it, this is pointing in x direction. Let's apply the boundary condition at y is equal to A, and an interesting result comes out. When y is equal to A, it says A sine HA has to be 0, which tells you that this HA has to be some multiples of pi, where m is an integer and it cannot be 0. Mathematically, m can be 0, 1, 2, 3, so forth and so on. But m is equal to 0 makes no physical, is just trivial. If m is equal to 0, then basically I have a function exy which is 0. And that basically says there's nothing existing. I'm not looking for that. So though mathematically m can be 0, physically this makes no sense. Or physically it's trivial. So m is going to take some integer values, which tells me that this h term is discretized. H is m pi by a, where m is some integer values. So this h term becomes discretized. It can only take certain values, it cannot be some arbitrary term. And remember, what was h? H square was omega square mu epsilon plus gamma square, and that is m pi by a square. Your gamma term is your propagation term. Gamma square was m pi by a square minus omega square mu epsilon. And again, remember, gamma was alpha plus j beta. Gamma is the term which contains the propagation constant, and it's telling you from this term, from this equation here, from this relationship, that the propagation constant can only take a certain discretized values. It cannot be any arbitrary propagation constant inside. And with respect to each discretized value, there is going to be a specific shape of the electric field. So what we have derived so far is saying that our electric field E for this TE wave, which is varying in x, is varying at some sign m pi by a y, and is pointing in x direction if you want to put the vector towards it. And the propagation constant which we are looking for, what is the solution? How is it propagating in z? How does this wave travel in z? That's what we are looking for. That takes certain specific values which are given by m pi by a square minus omega square mu epsilon. You notice here, this omega is the frequency of the wave. Mu epsilon, these two are the material parameters of the dielectric between the conductors. Omega is how fast am I jumping up and down, how fast am I changing my field, uh, how fast is my source changing in time. Mu epsilon is the material properties we have. And from your previous class, you know K is omega by square root of mu epsilon is the propagation constant for an unbound wave in a medium. And unbound is nothing but the plane wave. So it's saying that I have a certain discretized solutions. These solutions are discretized. I have certain discretized solutions, and each of these discretized solution is going to have a different gamma. When I have m is equal to 1, the gamma is going to be different. The gamma is going to be reduced from the value I have within the material. Gamma is going to be reduced by pi by a. When I go to my second solution, m is equal to 2, the gamma is going to be different. So each of these solutions, each of these values are traveling are going to be propagating at different propagation constants. And since the speed depends on the propagation constant, they're going to be traveling at different speeds. These are called the mode, and since we're looking for the guided ones, they are called the guided modes. Think of them as modes of travel. Let's put this in picture. If m is equal to 1, my function ex y is a sine m pi by a y, so it's pi by a y, and my gamma square is pi by a square minus omega square mu epsilon. That is the case. If I plot, what would it look like if I'm plotting it in x and y direction? Let's say this is x direction, this is y, telling me that the electric field is pointing in x direction, but its amplitude is varying in y, and its amplitude is going to vary as a sinusoid. So the electric field is going to point this way in xy plane. It's not going to be uniform as we had seen in TEM wave or plane wave. The amplitude is going to vary as a sinusoid. If m is equal to 2, my function now becomes a sine of 2 pi by a y. And if I was looking at that function, it's telling me when the electric field still has to be 0 at the bottom, the electric field will have to be 0 here too. But instead of going through one lobe, it's telling me it's going to go through two lobes. So it is going to take a maxima, going to go to 0 in the center, and it's going to take a minima again. So it's telling me as I go along the length of the electric field, along the length of my waveguide, I have electric field in the bottom half which is going to be pointing in the positive x direction, and in the top half I'll have electric field pointing in the minus x direction. This is called TE1 mode. This is called TE2 mode. Similarly, if I go to TE3, then M would be equal to 3 for TE3. And the solution is now going to have three lobes inside that waveguide. That's what this term really means. So it's going to have effectively three lobes like that. So the electric field is going to be pointing in this direction, but it's going to change directions for the other lobe and then come back to the same direction for the top lobe. Each of these solutions mathematically are the eigen solutions with their own eigenvalues, the eigenvalue being gamma square. Each of this distribution is traveling as a unique distribution through the waveguide. They don't interact with each other. Once I have excited one of these distributions will carry, they are the eigen solutions. So they will, if the waveguide does not change its shape, these solutions will not give their power to any other solution. These solutions will exist throughout the waveguide and will travel with their own specific, unique propagation constant. Do you have any questions? Any questions to understand this? If you don't, I have a question. My question is, where have you seen solutions like this before? This is something which, even as kids, if you play instruments, musical instruments, you see, but I'm sure you have seen this in your first year physics course. Don't these shapes look exactly like a guitar string connected, uh, like a string, like a string connected to two hard-bound wires, two hard-bound solutions? If I take a guitar string and connect them to two walls or string to two walls, and I start looking for what kind of resonances would I create, wouldn't the string oscillate either this way or this way or the third lobe and the fourth lobes? So if you notice, the form of this solution is exactly the same form you see in any resonances which happen. Guitar string being a very, very classical example. If you take a guitar string, it would only oscillate in very specific harmonic modes. That's how all these musical instruments or the pianos, the sitars, various other things are made to create only very, very specific frequencies, very, very specific propagations which can happen. And if you notice, we have two conductors. Those two conductors are almost like walls. Those two conductors are forcing the electric field to go to zero. If I have a guitar string between two walls, I'm forcing the guitar string to be held at those two walls. The guitar string cannot move away from those two joints. By having two conductors, I'm forcing the electric field to go to zero there. I'm creating reflections of the electric field right at those conductors, which create this resonance. We'll mathematically look at that tomorrow, and we'll see how we can represent these modes as summation of two plane waves which are interfering with each other. So let's continue with this discussion on the solutions. And the next question which comes is, do these solutions always exist? And the answer is, we have to look at the cut-off frequency. If I consider the solution for the TE mode, remember my gamma square is omega square mu epsilon minus, sorry, minus omega square mu epsilon plus m pi by a square. And we are looking for a solution which is E minus gamma z, which is of the form of E minus alpha z, E minus j beta z. I definitely need a term, I definitely need this term for wave to exist or to propagate. If this E minus J beta Z term is not there, I definitely I I am in trouble, which tells me that my gamma square term has to be a negative term. So this gamma square term has to be less than 0. So when I take the square root of that term, I get the imaginary part term out. Again, remember gamma is alpha plus j beta. And I definitely need this term. The wave is only going to propagate if that j term shows up. So it tells me that my gamma term, my gamma square has to be less than 0. The worst case has to be less than or equal to 0. So the worst case which can happen is gamma square is equal to 0. And at that frequency, basically I have minus omega square mu epsilon plus m pi by a square, or this is what we call the cutoff frequency, omega c, when that is equal to 0, is 1 by square root of mu epsilon m pi by a. This is called the cutoff frequency. When my gamma square term goes to be 0, if my gamma square term is positive, then I don't have any imaginary part in gamma. My gamma is only going to have a positive alpha part, and there is not going to be any E minus J beta Z term. So there is not going to be any wave propagating. It's just going to be an attenuating wave. It's just going to say that the electric field is going to suddenly attenuate as you go with Z. So if I was going to write my gamma in terms of my cutoff frequency, my gamma is square root of m pi by a square minus omega square mu epsilon. Let me take mu epsilon term out. So I can write this as square root of mu epsilon, square root of m pi by a square, 1 by square root of mu epsilon. No, sorry, 1 by uh, the square mu epsilon minus omega square. But this term is nothing but the cutoff frequency omega c. It's saying this is mu epsilon square root of omega c square minus omega square. I can take even omega out. I can write this as omega square root of mu epsilon omega c equals omega square minus 1. That is the propagation constant which I have. And this has to have the form of alpha plus j beta. So it's telling me for omega less than omega c, my gamma is just alpha. For omega less than omega c, my gamma is just equal to alpha, and the value of alpha is given by exactly omega square root of mu epsilon omega c by omega square minus 1. This term, when omega is less than omega c, this term is greater than 1, and thus this root is the root of a positive number and thus can only have a real value. So the wave, which is E minus gamma z, is only E minus alpha z. There is no propagating term. So it's telling me for omega less than omega c, the specific mode cannot propagate. That solution cannot exist when omega is less than omega c. When omega is greater than omega c, my gamma just becomes j omega square root of mu epsilon uh, omega c by omega square minus 1. Oh, sorry, not j, but just omega square root of mu epsilon. Omega c by omega square. And since omega is greater than omega c, this term is less than 1. So this is a negative value. So I can write this as omega square root of mu epsilon minus 1, 1 minus omega c by omega square. The minus 1 is j. So I can write my gamma as j omega square root of mu epsilon 1 minus omega c by omega square. And this is only true for omega greater than omega c. So this term is only a beta term now. And now the wave can propagate. So once the frequency becomes greater than the cutoff frequency, that specific mode, that specific solution can propagate. So if I was plotting this and if I was saying with respect to omega, at omega c for the first mode when m is equal to 1, again remember, what is omega c? Omega c is given by a term, and this cutoff frequency is going to be different for different values of m. So omega c is given by m pi by a 1 by square root of mu epsilon. So when this omega c is pi by a square root of mu epsilon, in this region, in the region below, TE mode cannot propagate. There is no transmission happening. You may have, I don't know if you have a lot of tunnels in your area, but if you go through a tunnel almost acts like a waveguide. And when you go through a tunnel, you will notice that your AM radio, the amplitude modulated radio, which is only running at few hundreds of kilohertz, 530 to maybe 1 megahertz, that AM radio transmission would suddenly stop within the tunnel. But the FM radio which is operating close to a gigahertz or so, or few hundred megahertz, yeah, in Canada it's about 98 to 100 megahertz. The FM radio transmission may still happen. The reason is that the tunnel waveguide, the AM radio frequency is very small. You are operating in this region over here, and the transmission of that mode doesn't happen. There's no mode allowed. There's no way electromagnetic field can create a distribution such that it can go through the tunnel, such that it can propagate through the tunnel. It is below the cutoff frequency and the transmission stops. Whereas the FM radio is above the cutoff frequency And the FM radio you can still hear to the FM radio even while you're going through the tunnel. So below this frequency, there is absolutely no solution possible. There is no propagation of electromagnetic wave happening. TE mode cannot propagate. And tomorrow when we look at the TM mode, you will notice that the TM mode can also not propagate in that region. So when we are looking for this, so below this, in this region, the TE mode cannot propagate. There cannot be any electromagnetic wave which can go through that. For regions above that, TE1 mode can propagate. You can have solutions. You can have an electric field distribution which will propagate with the TE mode. When you go to a different frequency now, omega C2, such that this is now 2 pi a by square root of mu epsilon. Below that frequency, TE2 cannot propagate. Whereas above that region, in this area, TE2 can propagate. So for omega greater than omega C2, such that it is greater than 2 pi a by mu epsilon, there can be two different solutions. Two different functions can exist at the same time, and each of those functions will have their own propagation constant. Each of those functions would behave independently of the other one. For omega, between 2 pi a by square root of mu epsilon and greater than pi a square root of mu epsilon, only TE1 mode exists. This is actually desirable for many applications. For that region, for that wavelength region, right here in this green shaded part, only a very single specific distribution of the electric field can exist, that is the TE1 mode. And this is important, and maybe we'll talk about it later in more details. This becomes important because when you're trying to send information through these waveguides, if the information is traveling through two or three different ways, and each way is traveling at different speeds, the information will get spread out, and that's called dispersion. The information will get spread out, and you'll start having errors in receiving that information. That's called intermodal dispersion. You will definitely see that when you do fiber optic communication. So for many applications, it's desirable to make the waveguide single mode. This is called a single mode condition, where only one specific mode of the solution can exist. So what we have learned now is, because we were confining these waveguides, the solutions we are getting are almost very similar to the resonances we see in any harmonics. We have created some kind of a resonance inside, so that there can be only very discretized distributions of the electric field. The electric field cannot take any arbitrary shapes inside. It can only take very discretized distributions, and each of those distributions is traveling at its own speed, and each of those distributions has its own cutoff frequency. Below that cutoff frequency, that distribution cannot exist at all. Above that cutoff frequency, the distribution can exist. Any questions? Right, let's do one small topic then. Let's see what is the phase velocity for a mode. We have already seen that for omega greater than omega c, when the frequency is larger than the cutoff frequency, beta is given by omega square root of mu epsilon 1 minus omega c by omega square. You know that phase velocity Vp is given by omega by beta, and you can convince yourselves omega is 2 pi f, beta is 2 pi by lambda. So phase velocity is omega by beta is 2 pi f by 2 pi by lambda is your famous function f lambda. So phase velocity is given by omega by beta. So that becomes 1 by, if I just substitute the value of beta, 1 by square root of mu epsilon 1 minus omega c by omega square. And again, omega c was given by m pi by a square, m pi by a 1 by square root of mu epsilon. So now one thing you notice here is this 1 by square root of mu epsilon is nothing but the phase velocity which is in the medium. The phase velocity of the dielectric Vt in the medium is 1 by square root of mu epsilon. Waveguide, phase velocity is now Vt in the medium divided by 1 minus omega by omega square. And you can convince yourselves for different modes, which means different values of m, Vp is going to be different. Each mode, each value of m has a unique distribution of the electric field towards it. And not only that, that electric field distribution is traveling with its own phase velocity, traveling uniquely from the other modes which are present, which could be present. Also, if you noticed, and this is something for you to think about and try to give me an answer in the next lecture. If you notice, this term here is going to be less than 1. This is 1 minus omega c by omega square. The phase velocity will only exist for omega greater than omega c. So this term over here is going to be less than 1. Telling you that the phase velocity in the waveguide is going to be greater than the phase velocity in the medium. The phase velocity in the waveguide is going to be greater than just 1 by square root of mu epsilon. And now comes the problem, because you basically say that the wave is traveling faster than the speed of light, or the information is going to travel faster than the speed of light. How does that make sense? What is the physical reasoning where it looks like to us that the phase velocity in the waveguide is going to be y is Vp greater than Vp medium, and how does it reconcile with the statement which you most probably have always heard: information cannot travel faster than speed of light? All right, let's stop here. So we've come to a conundrum here. When we calculate the phase velocity in the waveguide is going to be larger than the phase velocity of just the medium itself. But I, I hope everybody has heard the statement that information cannot travel at speeds faster than the light, and this is telling me, hey, if I make a waveguide and if I operate close to omega, close to cut off frequency, my phase velocity is going to be much, much faster than the speed of light, and maybe I'm able to travel information faster than that. Let's see, think about it, see if you can come up with an answer. Otherwise, I'll probably try to get an answer by another 2 lectures or so. So what we did today was we said, let's start looking for the electric field within a specific, the TE mode between parallel plate waveguides. We created the boundary condition that the electric field has to be zero at the two plates. And because the electric field has to be zero at the two plates, we found that the electric field can only take certain discretized distributions. Each of those discretized distributions has their own phase velocity, its own unique propagation constant gamma, and has a unique distribution which is independent of the other distributions. Each of that is an eigenfunction of my second order wave function, Helmholtz wave function, the eigensolution of the Helmholtz wave function. Tomorrow we'll take the solution and we'll add some more depth to it, towards it. We'll see what does the magnetic field look like when I have a solution like that. And then we'll extend it to the TM mode. The maths for the TM mode would be very similar to that. Instead of starting with electric field EX component, we'll start with the EZ component and we'll find the solution for EZ, which would turn out to be very similar to that. And then we'll look for what the magnetic field and the other electric field distributions look like. Any questions?
Sir, in EC1, when we don't have any question.
Okay. So I will again put the recording online and I'll send you the lecture slides.
Okay, sir.
And then we can
So,
talk tomorrow.
sending the videos through a YouTube channel or as a link, sir?
Yes. I sent you the link for yesterday's class online.
Okay.
I already did that. I think you should have it. I'll send the YouTube for this one also.
Okay, sir. We will meet them.
Okay.
Tomorrow we'll meet it at the same time, 8:45, sir.
Yeah, same time.
Okay.
So, sir, can you hear me?
Yes.
From Mr. Sona. So, students want to know that YouTube channel again. Sorry, they didn't listen yesterday, it seems.
Okay, I'll send a link to both Jaya and you. Why don't you just
Thank you.
distribute that link?
Okay, sir.
I'll send the link out today,
Okay.
and you just distribute the link to the students.
Fine, sir. I'll make
Okay,
that.
sir.
Okay.
Thank you. Thanks so much.
All right.
Have a nice day.
You too. Okay. See you tomorrow.